My name is Jongouk Choi. Today I will briefly introduce myself and my research group, and then I will introduce my current research topic, which is loading non-volatility in non-volatile memory. I'm a assistant professor, computer science department in cybersecurity private cluster. I received my Ph.D. from Purdue University and major in computer architecture and compiler. I'm a compiler and architecture code designer. With the code design approaches, I'd like to reduce hardware complexity, but improve the performance and address reliability, security problems. Before joining UCF, I used to work on research, electronics, and so on in industry. I'm currently leading compiler architecture Compark lab. My lab at UCF is working on some projects in computer architecture and compiler area. And we are currently exploring in non-volatile memory-based systems that have been adapted to energy harvesting applications, general purpose computers, and server computer as well. My teaching activity, I'm teaching CDA 3103, Computer Logic and Organization for undergrad students. I will teach CDA 5106, Advanced Computer Architecture for graduate students. And then let me briefly introduce my current research topic. Non-volatile memory is on the rise. Intel, Micron, Samsung, lots of manufacturers are paying attention to this memory. Many researchers introduced various types of non-volatile memories: phase-change memory, STT-RAM, FE-RAM, FVRAM, MRAM, and so on. The main reason why there are many technologies are emerging now is they can operate at low power, yet still have very high densities, biodistributable and durable, and they're approximately 100 times faster than disk memory. And thanks to the benefits, researchers adapt this non-volatile memory as main memory for various systems, enabling a wide range of applications. For example, nanosatellites are one of the rising applications these days. Since the satellites are too expensive to manage, people leverage low-power computers like IoT devices to develop nanosatellites running in our space. The main challenge of this nanosatellites is the battery. Since the lifetime of a battery is about 2 to 3 years, people should go to the space and replace the battery every 2 to 3 years, which is really impractical. To address the challenge, researchers have adapted energy harvesting technology to self-power the nanosatellites using solar energy for free. Moreover, since the solar energy can be unstable sometimes, they have adapted the non-volatile memory so that the data can be persistent always. Another application, implantable medical devices such as glucose monitor or heartbeat monitor, unfortunately, is not easy to access the devices also, since the devices are actually implanted inside a patient's body. To address the challenge, people use non-volatile memory and energy harvesting technology as well, so that the devices can be self-sustaining and maintenance-free. These types of technologies have been widely adapted to other applications as well, from wearable computing to the server systems. However, there's no free lunch. We cannot magically enable the applications by having these non-volatile memory technologies. The systems have a critical challenge, which is crash consistency. If power failure crash happens, the systems can suffer from permanent data corruption in their memory. This is because in contrast to non-volatile memory, the processor itself lose all volatile data. In other words, the processor and the main memory cannot be in sync across power failure. They can produce the wrong output at the end. To deal with this issue, one of the major manufacturers, Intel, introduced an EADR mechanism, enhanced asynchronous DRAM refresh. It basically monitors the voltage level in the circuit, and then once the voltage drops below a certain threshold, it flushes or checkpoints all volatile data and cache lines to designated space in non-volatile memory by spending some reserved energy in capacitor or a battery. Let's briefly see how it works. On the right-hand side, you can see a processor design. When we have voltage monitor and backup recovery model and battery or capacitor in the chip, we have L1, L2, and 3 caches in the processor. When the voltage monitoring system detects impending power failure at a certain voltage threshold, it signals the core, then the core checkpoints all volatile data to non-volatile memory and power off. Then in the wake of power failure, the core restores the checkpoint data from the non-volatile memory and resumes the interrupt program. By having this EADR technique, the processors can give an illusion that they are like a non-volatile processor and maintain all data persisted across power failure. Existing non-volatile memory-based systems use this EADR technique. However, we found that they assume that a battery or capacitor is always reliable. Unfortunately, it's not true. The battery or capacitor can be degraded, losing their original capacity by more than 20% regardless of their size or material. It can be cracked or damaged by some possible conditions: temperature change, humidity change, continuous charging and discharge condition, and ripple current. In this case, the amount of reserved energy can be less than it's supposed to. Then with this insufficient amount of reserved energy, the EADR fails to persist all volatile data, thereby losing data across power failure. We define such a problem as capacitor error. To address the capacitor error problem, we introduced the capacitor error resilience solution. There are actually two types of possible approaches: proactive solution or reactive solution. First, a proactive solution can be suggested by reserving more energy for checkpointing. However, the proactive mechanism cannot be a practical solution because the reserved energy can only be used for checkpointing, not for program execution. Moreover, since the battery or capacitor can be degraded continuously, the proactive approach cannot solve the problem eventually. On the other hand, the reactive solution is hard to be realized. This is because it detects the capacitor error problem after the problem happens, leading to data corruption eventually. In other words, the solution cannot prevent data loss from the capacitor error. To address the capacitor error problem, we introduced a CabOS operating system-driven capacitor error resilience solution. CabOS can detect the capacitor error in a reactive manner by having an ACK message as a barrier of checkpointing. For example, CabOS checkpoints the ACK message as the last part of the checkpointing protocol as a barrier. So if capacitor error occurs, the processor fails to checkpoint the ACK message only, preserving all other volatile data. This is possible because the capacitor or battery is gradually degraded, not cracked all of a sudden. Upon the detection, CabOS changes operating mode to ensure program execution without relying upon the battery. As a result, as you can see in this slide, right-hand side corner, we found the capacitor or battery can be degraded by more than 10% within 30 hours. And it can eventually cause the capacitor error. We found our scheme can protect all data from the capacitor error. We also measured the throughput of our scheme, CabOS, and compared to the other schemes, proactive solution called Samoid-S, a reactive solution called Chinchilla in 3 different cases: reliable case, unreliable case, and extremely unreliable case by having frequent power failure. It turns out that in all cases, CabOS can continue to provide quality of service in contrast to other solutions. From experience, we found the CabOS costs less than 1% performance overhead. CabOS always ensures error-free execution, while all prior works are vulnerable to the capacitor error. We further explore the capacitor error problem in security domain. We found that attackers can exploit the capacitor error for security attacks. For remote attack, if attackers can spoof or interference in power signals by using power jamming device, they can generate malicious voltage fluctuation in the logics, which is another possible condition for capacitor error. We call such attack as capacitor error. We also evaluate our hammering attacks as shown in this slide. The attack can be launched within a day. Once the attack is launched, the victim or device cannot produce the correct output. As a result, we found the hammer can cause 4 security implications. Data corruption is the one that I mentioned before, abnormal termination, and denial of service. Moreover, hammer can disable data encryption solution in modern computer architecture, which is also a serious problem. To defeat the attack, we also exploring 3 possible solutions: hardware solution, software solution, and hardware-software co-design solution. Now I'm exploring this security problem in various applications. For example, biomedical devices, glucose monitor use the same technique as I mentioned before. If attackers can nullify the device, they can cause a life-threatening problem. Not only the data corruption, but also the denial of service is possible. We can also think of possible side effects in biomedical area. NATO satellites and unmanned vehicles will be crashed once the attack is launched. There are our future works. And in long term, we're going to attack server system like a banking system. If the banking system lose their data in their memory, it'll be a critical problem also. Since the hammer attack can also nullify the data integrity confidentiality support in server systems, it could be a critical issue as well. My work has been done with my colleagues from many different institutions and supported by NSF and at one of the national labs in South Korea. And if you have any questions, please let me know. I'm happy to be a part of College of Engineering and Computer Science in UCF. Thank you.